ladies and gentlemen. Welcome to the International Seminar on Energy Production from Waste, Landfill and Dumpsites hosted by the Urban Unit and Lahore Waste Management Company. Ladies and gentlemen, waste management is becoming a large-scale problem, especially with the growing population and increased urbanization. Hence, more energy is required for the population and economic growth. Energy production from waste is a promising alternative to resolve both these issues. In this regard, Pakistan has immense potential due to high volume of waste and its technical capacities to build these systems. I would like to invite Mr. Azhar Ali, Senior Solid Waste Management Specialist, Urban Unit, to present his views regarding waste management sector in Pakistan. Mr. Azhar Ali, please.
Thank you, Ms. Sara. As Ms. Sara told all of us that waste management and energy, they are interconnected. In one side, we have a huge problem to manage all the waste being produced in the country, and on the other side, we have a huge deficit for our energy. So that's why I call, if we can couple these two issues, it would be quite feasible for us to get rid of both problems. In this regard, what I see is that technology already exists. Know-how already exists. There have been several very successful interventions throughout the globe. There was a good chance that I could have brought a leading company from Germany to tell us what they are doing, or from Japan. But I would not go for that, because we are a few hundred years back in waste culture as compared to those countries. What I found is that very close to us and very near to us is the country of Turkey, where I have spent more than 2 decades. And so I found several companies bringing in solutions. But on top of them was ITC from Turkey. Never underestimate this company. They can even build a landfill and produce energy at the moon and bring it back to Pakistan. So I request all of you to listen to their presentation, whether it's technical or informative. But I foresee that if we can get their cooperation, or if we can get the solutions similar to what they are introducing, we won't lose a lot of time, because we are trying to invent the wheel for a long time. Waste can be converted into energy, that we know. Whether it's fermentation, whether it's incineration, whether it's gasification, all these processes are actually made for different types of wastes. And ITC holds its distinction that it was able to produce, it was able to test all these technologies for the waste type, which is very similar to what we have in Pakistan. So in this regard, I look forward really and very sincerely that we would have a long-term collaboration on company to company, or maybe on government to company, in some way, that this problem of energy and this problem of waste management can be solved using the techniques and the processes they have been applying in Turkey for more than a decade. So I wish all of you a very fruitful session, and hope that you will stay till the end, because we have placed their presentation at the end, so that the best comes at the end. Thank you very much.
Thank you, Mr. Azhar. Waste-to-energy facilities have been established in various developed nations, which most of the time involve complex technology. Numerous efforts have been made to produce energy through biogas or waste dumps in Pakistan also. A plant was successfully established at waste dump site of Rawalpindi that clearly indicated that simple technology has a promising future. I would like to invite Dr. Usman Hanif, who has extensively worked on waste-to-energy technology and holds his PhD in waste pyrolysis, to provide information regarding case study of waste-to-energy projects in Rawalpindi. Dr. Usman Hanif, please.
Bismillahirrahmanirrahim, and Assalamu alaikum to all of you. My name is Usman, and I hold a PhD degree from Texas A&M in Nast, Pakistan. My basic degree was in integrated system. Like she said, that I have done my degree in pyrolysis, but it was not in pyrolysis. It was an integrated system that holds like 3 to 4 technologies together, and then we produce the energy, like a complete solution, like the other guys, like ITC will tell in their presentation. So I am presenting here a case study that was done in like 2013 when I was like immature guy regarding this waste to energy project. So I just let you know about what is a waste to energy and how we can generate some energy with some indigenous materials. For example, if you say that there's a gas that is produced from a landfill is called landfill gas. Mostly it is like 2 types of mixtures, that we have some amount of carbon dioxide and some amount of methane in it, and we have also some trace amount of other gases that needs to be separated out. But mostly that the 2 mixtures are methane and carbon dioxide, both are 50%, and methane is the useful component of it. Secondly, the important aspect of landfill gas is that you have to capture it. You have to dig something and then you have to capture it. In Pakistan, the uncertain issue is that we have almost all of the open dumps. Like these people will also come to know that it is not like other countries. We have all the open dumps, all the gas escapes into the atmosphere, and then we have to plan it. So I was fortunate enough that in 2013 I was managing that landfill site. So for 2 years and 2.5 years I have continuously managed that site. Then I have dumped the waste and then I have collected it out. So if you go by the world scenario, you will find that most of the landfill sites, like 50% of landfill sites, are now capturing that landfill gas and then converting into like energy or some other sources. If you go by the Rawalpindi landfill site, you will come to know that it was started in its operations in 2006. Its total area is like 22 acres of land, and it is now almost full, as MD or WMC is also sitting here. And he was discussing with me a little while ago that we are planning for a new landfill site as well. So that area is now mostly covered, and it is covered because we have dumped irregularly, not in a professional manner. If we have done in a professional manner, that landfill site may have lasted up to 2030 as well. So if you go by the facts that how much landfill gas is now producing inside those small or irregular dumps, then you will find that 26.3 million meter cube of gas was producing in 2013, according to that amount of waste that has been deposited over there. And by 2023, you will find that 93 million meter cubes of biogas can be recovered from that landfill site. So by going those facts, we have established a small pilot scale plant over there. So we have calculated that how much energy we can easily produce. Then we have calculated that it was around 5 megawatts of electricity that can be easily produced by capturing that landfill gas. Next. So this is a typical graph that every environmental engineer must know, that how this waste changes after being placed in the landfill site, then how these carbon dioxide ratios changes and methane produces. If you see the methane curve, it is the most important, that there are 4 phases. In the first phase, you will have high amount of methane because we have some inoculum produced there. Then they go in decreasing manner, and after a while, that methane is stagnant up to somewhere, like after 4 years or 3 years. Next. This is a typical model that always used, that how landfill gas is recovered. You have a good covered landfill site with some protection over there. Then you have a vertical system or a horizontal waste nets that collect the landfill gas, and then they pump it out. Then they generate electricity after purification from some methods, like the trace amount of gases are removed, and then they are produced and electricity is given to others. Next. If you see the compositions I have shared here, this is also published in international journals as well. You will find that there are 3 types of mostly the waste that comes into a city. One is the household waste, second is the restaurant waste, and third is the mixed waste. And if you see the composition, you will find that most of the items are green waste. So they have the tendency that they will produce methane when they will be placed in the landfill site. One. Secondly, you have to see that there are other options that you can play with them. And also you have some recyclable materials, and also some materials that have good calorific value. So you can use other technologies of waste conversion as well. Next, please. And these are some of the pictures when we studied over there. I was also a PhD student, so I have to go with scientific methods as well. So this was the condition in the of the Lahore landfill site. Then we used some testing protocols over there and then tested over there. Next. These are the status of the landfill site. So the total waste at the site in 2013 was 1.7 million tons. The gas that can be available was 3180 meter cube per hour. Okay. Then how much capacity that we can generate from that is around 5 megawatts, because we were producing around 60% of methane from that combination. So if you go by the facts, then you will see that in biogas you can produce like 2 kilowatts of 1 meter cube of biogas can produce 2 kilowatts of gas, and for 1 meter cube of soy gas, like the original gas that has 98% purity, can be produced 3 kilowatts of gas. In our study, we copied this left side extraction well, and we have placed that same well into the ground, and we have created around 7 wells in a subsection of a landfill site where we have created it. Next. This is just a sample that how this collection system is being separated in good landfill sites. So we divide the landfill site into cells and then subcells. Then we place the collection material, and then how we extract the gas. This is the typical formation that how we can extract those wells. Next. So this is the basically our pilot plant, which remain in operation like up to 300 hours in Lahore. We have digged 7 wells. Then that well was connected to a purification device, a small pipe you can see in the white color. Do you have a okay, you can just see the on the extreme left of it is the pipe, white color pipe. It is of UPVC that has been filled with iron particles plus sawdust plus some chemicals that basically remove hydrogen sulfide. When we tested this, then our results came that we have removed up to 70% of the hydrogen sulfide. But there are methods that where we can use and remove like 90 or 99% of hydrogen sulfide as well. Then we have a filter over there. Then we have a small compressor that compresses or sucks the gas from the wells. Then it goes into this storage, yellow color storage material. Then it stores over there. And after that, there is a condenser that removes the water particles into it. And then we have 2 types of regulators to maintain the pressure for the generator. Then we have a generator of 135 kVA. And then we have produce energy over there. The right side is the condenser that cools the engine for the continuous operations. So when I was like immature in 2013, then I've created this thing, and we have lasted this operations for around 423 hours, and we have given this electricity to a nearby village as well. Next. At that time, there was a provincial minister, Mr. Sher Ali, who came to us and he said that we have to make this plan more workable. So we have to go by the economics of that 5 megawatt plant. If you see by the initial years like 2013, 14, 15, 16 and 17, up to 2018 we have to recover that amount of 0.792 billion that has to be invested to create this 5 megawatt of energy plant. And then if we have a tariff of 4.15 per kilowatts, that they will be purchased by NAPRA, and then we can collect back that energy, amount. Then we can recover the capital cost of this plant by 5 years. And after that, we have this all surplus years, like up to 20 years, we can easily extract the energy, and also we can make good amount of money. Next, please. So if you just go by the power plant comparison, you will find that this chart is showing the millions of US dollar per megawatt. If you see that there are different types, like hydel is very costly, then wind, solar, thermal, coal, and last is the landfill gas, because in the landfill gas you do not require any fuel. You have already an available fuel, and then you need generators and setup, and then you can go by it. Next. This is sir, for you. This is a very important slide. So I calculated on the basis of that how much waste we have in different cities of Punjab. Punjab is the province of Pakistan, and inside Punjab, how much is the potential that is available. This slide is also modified with your technology as well that ITC produces. So we have initially जो potential of 220 megawatts for only Lahore, that has a capacity of around 5,000 tons per day. So this slide basically shows that how much potential we have in megawatts, and if we go by only this landfill site. There's another good thing about municipal solid waste to energy is that if you go by these waste to energy technologies, then you can easily limit this waste disposal issues. Secondly, you can also manage your landfills for much longer time of period. For example, if you do anaerobic digestion plus some pyrolysis for the waste, you will have been left with only 20% of the waste that will be going to landfills. So if you are dealing with 20% of landfill side waste, then it is much more cheaper than 100%. So this is how this goes. Next.
Lahore Waste Management Company has been involved in not only cleaning the city through effective waste collection and transport, but also plays an active role in bringing new innovations in the system. I would like to invite Mr. Rizwan Saeed from Lahore Waste Management Company to provide us information regarding biomethanization of organic waste at biogas plants of Dunyapur and Lodhra. He is working as manager treatment and disposal at Lahore Waste Management Company. Mr. Rizwan Saeed.
Assalamu alaikum. My name is Muhammad Rizwan Saeed. I want to present biomethanation, please. Case study of establishing biogas plants at Lahore and Dunyapur. Next, please. This is the background of biomethanation. First of all, history of biogas in Pakistan about 42 years. 1984. Starting government of Pakistan to establish biogas plants in Pakistan, and round about more than 7,000 digesters repeatedly installed across the country, in which LGNCD, local government and community department assigned with LWMC to establish 7 biogas plants in Lahore, Dunyapur, Chaniot, as well as in Bahawal Nagar, in which first of all 2 biogas pilot plants in village 342 WB and 327 installed at Lodhra, and 1 Ichogil Uttar biogas plant. These biogas plants have capacity 200 cubic meter per day. This is the history of biogas technology in Pakistan. First of all, government of Pakistan started comprehensive biogas plants around but more than 4,000, 1974 to 1987, to establish biogas plants. And then after that, different NGOs like 200 and 2,500, as well as install in United Nations Development Program 150 biogas plants, as well as in 2007 12 biogas plant established. This is history which is I collect the data from search of history of biogas plant, United Nations Development Program, which survey report, which feasibility study of the biogas domestic 2007. Next, please. LWMC survey, about 25% biodegradable material in landfill site is available, in which biodegradable material waste, kitchen waste, rotting fruits, vegetables, peeling, vegetables, fruits, animal waste, plants, biogas which is available, and biodegradable waste converted to useful energy instead of the throwing to disposable site. Next, please. This is the ISTEC survey in 2012 summary, in which 65% organic waste available in landfill sites, which we want to convert into the suitable consumption like biogas plants, which we want required. This is the raw material, basic how we can produce biogas from these raw materials. Organic waste, as well as sludge, animal manures, and plant biomass, which have ability to produce biogas to convert into the suitable energy source like biogas, as well as fuel, heat, kitchen, and other things we can use these energy products which we want. Next, please. Biomethanation, how can we define biomethanation? Biomethanation is scientific process in which we can microorganism break down into in the anoxic environment to decompose to the anaerobic digestion to convert into the organic material. And normally this is naturally occur in swamps, peat bogs, lakes, ponds, hot springs, in which we can produce biomethanation normally maximum in, as well as in intestines of the ruminants. This is the graph of biogas production from organic material. Normally cattle slurry which we used in this have the capacity of 19 cubic meter per ton of animal waste. If we deeply study the grains as well as corn cob has a more capacity of the biogas production as compared to cattle's pig slurries. This is a survey which shows that the cattle slurry is 19 cubic meter per ton of production, and then we produce most feasible for in this environment in Pakistan, especially in Lahore. This is the biomethanation process. First of all, hydrolysis process, acetogenesis, acetonegenesis or methanogenesis. In first case, hydrolysis process in which जो हमारे polyesterides convert into the small monomer, soluble monomers like sugar, fatty acids, amino acids, and then in this acetogenesis process, carbonic acid, alcohol, hydrogen, carbon produce. And then after that, the last stage is the methanogenesis, in which methane as well as slurry, which have more than 90% water and remaining part organic and inorganic material which is present in their biogas. Next. This explanation of the stages of the hydrolysis. The main factors of biomethanation, these are 7. pH, that is a very important factor in biomethanation process. Normally, optimum range in biomethanation process normally 6.8 to 7.2, which is suitable. If pH value shows acidic form due to the carbon dioxide production as well as fatty acid production, which show the characteristics which had the biomethanation process. That's why the optimum condition of the pH, which is light to 6.8 to 7.2, and temperature which is most feasible or suitable is 35 to 37 degrees centigrade, which is more suitable for the production of methane as well as proper mixing which prevent the ammonia formation, which also represent the production of the methane as well as organic hydraulic retention time and nitrogen carbon ratio. This is the composition of the biogas, in which methane normally in this area 50 to 75%, carbon dioxide 25 to 50, as well as hydrogen, water. In this biogas which we established in Pakistan, especially in Ichogil as well as in Duniapur, we observed that the percentage of carbon dioxide is more. That's why it's not improper combustion, and as well as due to the lack of in this range production of the methane, not proper combustion which is observed. That's why the we want to also progress to decrease the percentage of the carbon dioxide which lie in this range. This is the characteristics of the biogas. Density 20% lighter hai, as well as ignition temperature, blame just like blue color, same like LPG, and calorific value as compared to the natural value is more half, as well as biogas has the capability to produce electricity, 1.5 kilowatt of electricity. In Ludhiana Shahar, where around about 5,000 cubic meter per day production, and they are producing 1 megawatt per hour production of the electricity, and normally 12 to 13 hours biogas plant operate, and they are producing 12 to 13 megawatt per day of the electricity. This is the waste disposal strategy of LWMC. The green shows that we have achieved, and next we are achieving in red color showing that we are search work. On this stage we are on the pilot basis of the biogas. We want to upgrade on a high rate capacity of the biogas. We are studying and feasibility reports also creating. This is a flow sheet diagram of the biogas production. In this, first of all, biomass, which anaerobic digestion will produce biogas as well as fertilizer. Fertilizer is the byproduct of anaerobic digestion, where fertilizer also used for crops, for the producing crops, as well as through biogas we produce electricity as well as heat purposes to convert to the consumer and recycling to the biomass. Objectives of the biomass plants: better management of the disposal of the animal waste. And the second, reduction of the greenhouse gases to save the environment clean, clear. For the main purpose is the energy recovery and biofertilizer. In this regard, most of the time, the curtailment of the pressure of the formation of the wood fuel, which is also main thing. Next, please. Normally in Pakistan, on pilot plants are established normally 10 to 200 cubic meter, which we can say in small scale. And normally two types of techniques which used: fixed dome anaerobic digester and floating dome anaerobic digesters. First, we observed that in fixed dome anaerobic digesters, normally leakage of gas observed. Now we are going to shift into the floating dome anaerobic digesters, in which maximum attain of the biogas. We have potential to produce maximum storage of the biogas. This is the process in which normally on pilot stages we take normally 50% animal cow dung as well as 50% water to mix, proper homogenize, and then convert methane, produce a major product 50 to 70%, as well as the byproducts mixture of gas, carbon dioxide, nitrogen, which also produce. The biogas slurry is one of the end product of the anaerobic digesters. Slurry, which is used for biofertilizers, this slurry has normally 93% water and remaining 4% organic material as well as 3% inorganic material. Next, please. The further explanation: 23 to 30% matter of the animal waste which convert into the combustible gas, and remaining 70 to 75% solid contents of fresh dung comes into the slurry. This slurry has 93% water, 7% matters, organic and inorganic. The major nutrients: nitrogen, phosphorus, and micronutrients, zinc, organic, manganese. Next, please. This is the modification plant which we attain in check number 327, convert into the fixed dome anaerobic digester to the floating dome digesters, in which we observe the leakage of biogas from the fixed dome, the addition of the air, improper combustion which occur, as well as design modification to convert floating domes and enhance the biogas potential in this regard. This is the table of the biogas plants, in which 3 biogas plant having capacity 200 cubic meter, same capacity 200 cubic meter per day. And first installed 7 July 30, normally 14.84 million. The Ichugil biogas plants, and remaining same to 8.63 million cost. Next, please. Status: construction phase 4 months, which is almost completed, and operational after the completion and acceptance of the operation 6 months, which is an ongoing process, as well as maintenance after the completion. Normally, project is at initial operational stage. However, LWMC not issue the certifications, the acceptance to its contractor. Next, please. Normally, this biogas plants on the cost sharing basis, 70% LWMC pay to install these biogas plant and 30% the community based. Land as well as the recovery of the gas bills on base of the community, which have the also community governing body which recover the biogas bill. Next please. The issues which we face in biogas plants, unable to meet the quality and quantity of the biogas plant which we require. Normally 200 cubic meter per day is the main capacity, but unfortunately during installation of this biogas plant, no 200 capacity meet, and as well as deficiency in the quality of the required feedstock. In Dunyapur P27, the quantity of the biogas for the production of the biogas 200 cubic meter per day. The cow dung capacity as a feeding material normally 1.5 ton to 2 ton per day. But collection of the cow dung in per day normally 300, 400 kg. That's why in this regard production of the biogas so minimize, as well as leakage, community issues, quality of the biogas is not good due to the high percentage of the carbon dioxide present in the biogas, as well as digester wall cracking. Next please. At the end, the question arises, struggle of 42 years, 7,000 biogas plants established, which have potential 5 million of the plants. Where is the bottleneck? The main thing is that our lacking of the study on the biogas, and as well as we not upgrade their biogas plant into the large scale. No awareness of the technology, no training in this regard, no follow-up address to the problems. To improve the quality of the feedstock, R&D activity, as well as some conduct the training sessions to provide the technical advisory services to meet, to enhance, to meet in the upscale level, as well as learn from the international experience. Thank you for the presentation.
Pakistan is unfortunately still facing a big problem regarding safe final disposal of waste. Most of the waste ends up at wild or open dump sites along main highways or in periphery of the cities. Some of such dump sites have become quite large, and Mahmood Boti dump site in Lahore is among the largest dump sites in Asia. Its rehabilitation and energy extraction potential is very high. I would now request Mr. Naki Iqbal from Lahore Waste Management Company to provide facts and figures about Mahmood Boti Waste Dump Site. He is working as Project Management Specialist at Lahore Waste Management Company. Mr. Naki Iqbal, please.
Assalamualaikum. My name is Naki Iqbal, and I am Project Management Specialist at LWMC. I am going to present the rehabilitation of Mahmood Boti Dump Site and its energy potential. Next, please. Mahmood Boti dump site is one of the oldest dump site in Pakistan. It was operational from 1997. Its estimated area is about 320 canals, and the dump is about 13.4 million tons. Its biodegradable fraction is about 55 to 60%, which is a very good fraction. The site has reached around up to 80 feet from the ground, and there are uneven slopes which we need to cater off. The operation at the dump site was closed on 12th of September 2016. Next, please. Now, what is the objectives of the project? The objective of the project is to rehabilitate the site and finally convert it into the park or something like that. The following are the major components of the project. First of all, the cutting, leveling and compacting of the site. Then we'll give the soil capping and covering at the site. Then installation of gas vents, collection and treatment, and finally the disposal of the leachate. And then the provision of drainage system, and then finally the plantation and landscaping of the project. Next, please. We have divided the project into two phases. In the first phase, we have done the topographic survey, the cutting and leveling of the front side of Mahmood Booty, then the installation of gas vents, and then soil capping of front side of that. And in the phase 2, we will first of all done with the conceptual design. Then there will be a cutting, leveling and compacting of all the area. Then installation of gas vents, again soil capping and covering of the complete site. Then the leachate collection and disposal, and finally the treatment as well, and then landscaping and plantation. Next, please. So these are the tentative timelines of the project. First of all, the procurement of first component phase 1, that was done in September 2016. Then construction of first component of phase 1. It's completed in first week of November. Then the procurement of second component of phase 1, that will be in December 2016. Then construction of second component of phase 1, that will be completed in May 2017. Then the procurement of phase 2, that will be done in September 2017, and finally the construction will be completed by March 2018. Next, please. Now, what are the advantages of rehabilitation of these dump sites or the landfill sites? First of all, the controlling and reducing the order of before the rehabilitation of work. So we have done the work in 2 terraces. We are constructing 2 terraces at Mahmood Booty because there was a huge hump, as I already said. It was about 80 feet from the ring road level. So we are doing it in 2 terraces. Next, please. So this is the picture of the Mahmood Booty after cutting and leveling of the site. Next, please. This is the comparison before and after the cutting and leveling work. Next, please. Again, this is the picture. Now, these are the composition of municipal waste at Lahore city. It was done by our consultant, Istach. This can be seen from this slide that there are about 64.85% of biodegradables in the municipal solid waste. This is a good percentage, and we can convert it into the energy by this. Next, please. These are some of the overall compositions of, we have done 3 different compositions, or you can say the studies at 3 different levels, and these are the percentages. Next, please. So this is the gas potential at Mahmood Booty. This was done by Istach, and here you can see the CH4, the methane percentage. This is around 55% of the total gases. Next, please. So the composition, CH4, it is about 55.7%, CO2 is about 38.8%, O2 is about 0.5%, and H2S 5 ppm. Next, please. This is the pictorial view of the analyzer which was brought by Istach at the site. This is the electricity potential of Mahmood Booty dump site. In 2016, it was done by Istach. There is a 3,258 meter cube per hour gas capacity. Then electricity generation will be 5.66 megawatt per hour, and same is the case with other years. Next, please. So there are 2 different gas collection systems. As we have seen from the study, there is a gas potential in our Mahmood Booty site. So we are going to do the gas collection and installation of gas vents at Mahmood Booty. There are 2 different types. One is a vertical gas vent system, and other is the horizontal gas vent system. Next, please. The vertical gas vents are installed in the areas mostly where the site has stopped receiving waste or where the waste filling will not occur for a year or more. There are different components of this vertical gas vents. One is the HDPE pipe, next is the gravel, and then the steel mesh, which is somehow necessary. In Mahmood Booty, the vertical gas vents are proposed. Next. Horizontal gas vents. Horizontal gas vents are installed in the areas where the site has still receiving the waste. So their components are HDPE pipe, gravel, steel mesh, and there will be a geotextile layer as well. Next, please. This is the pictorial view of installation of gas vents at Mahmood Booty. Next. So what is the way forward? The picture shows that what is before the rehabilitation work and what will we be expecting after the rehabilitation completion. Thank you very much.
Thank you, Mr. Nakik-Pal. I hope that this presentation would have clarified various issues about the dump site and provided the necessary information to make any successful intervention. Turkey has achieved great success in developing indigenous technological solutions for waste management. Turkey has not only developed gas extraction and energy production facilities at wild dump sites, but also established highly sophisticated dry digestion and gasification systems for waste management. I would like to invite Mr. Ali Kantur to provide us information regarding rehabilitation, energy production from dump sites, and integrated waste management projects in Turkey. He has been involved in more than 10 waste to energy projects in Turkey. He is among the pioneers of research, development, and implementation of localized technology in this regard and is among the most powerful CEOs in the world. Mr. Ali Kantur, please.
First of all, I must thank you for this most powerful CEO. Anyhow, myself and my colleague Erdogan, we are very happy to be in a brother country and at the same time to be in, according to us, the most important city of this country, in Lahore. Now, the reason why we are here, because I've been not to Lahore, but to Pakistan in different cities before, I always felt at home. When I see you, when you see me, we know that we are like brothers. So we feel very, very comfortable to be here. Since I was introduced as such, I have to tell you a little bit about our backgrounds, because it is important that I have to tell our background a little bit. Before this waste business, we have been involved in many different businesses. Not only involved, but we had the chance of establishing those businesses in Turkey. Like in Pakistan, especially in those days in Turkey, I started to work in 1974. Most of you were not perhaps born in that day, but in those years. When we started, there was not much industry in Turkey. So whenever we established something, it was the first. So we were really, boasting about establishing the first furniture plant, the first door plant, first window frame plant, first prefabricated housing plant, first cement board plant, first gypsum board plant. One of the first terminals of Turkey, we built Istanbul Terminal, Atatürk Terminal, in 22 months' time. It was a BOT project. Then we built Esenboğa Ankara terminal. We built the duty-free stores. We built the first sports clubs, first city of Turkey, completely built, from kindergarten to universities, from offices to houses, to sport clubs, to shopping centers, the first shopping centers of many cities in Turkey. I forget some of them. The power plants, the first mobile power plants, and we have built 1/3 of the pipeline coming from Tiflis to Ceyhan, and also the pump stations, etc. Many other things that I cannot remember, around 40 different companies in different sectors. Then we ended up in this waste business. When somebody asks me, what do? I immediately say, I am a garbage man. This is my most favorable business. Why we have started this business? When we first encounter with this type of problem in Ankara first, actually I didn't want to go into this business because I knew on the way to airport there was a landfill, not a landfill, dump site in those days. When we approached this dump site about 2-3 kilometers, we had to close the windows. We have to stop the ventilation of the car. So I could not dare go in there without protection of the car, breathing the dump site smell. I really didn't dare. But what happened? Suddenly, on a trip, somebody whom I cannot remember told me a joke. I like jokes a lot. It gives flavor to the life. I want to tell you this joke. One day, two planets somehow are talking to each other. The first planet tells the other one, I have an incredible problem, a huge problem. The second planet asks, what is this problem? The first planet says, unfortunately, human being started on my planet. Then suddenly we started to think, what do we do to our planet? We really make a lot of bad things to our planet. We kill other animals. We make a lot of waste. We destroy the water. We destroy the plants. We destroy the atmosphere. We do many things. And we are intelligent animals, but still we may do such bad things to the planet. The second planet is very experienced, and he says to the first one, don't worry, leave them alone. In 10,000 years, they destroy themselves. So we want to have this 10,000 years, a little bit more years added to this 10,000 years. So we decided, together with my colleague, to see this dump site. This is how our story started. Then, what happened? Normally, like we had experienced before, if you want to establish a new idea, a new factory, a new plant to your country, what you do is, unfortunately, you go to developed countries. Even we go to developed countries to get education. Further education, further knowledge. So we thought we would do the same because we were experienced enough to do such plants, such factories. So we've been to Europe, we've been to the United States, to Japan, to all over the developed countries around the world. In fact, we have even bought some plants from them, some machinery from these countries and companies. But what we have seen that, unfortunately, some of these technologies, almost all of them, but I would like to say some, were not working. Some of them were too expensive to have a sustainable solution to our kind of waste. What was the difference? The difference was our waste content is different. Now we are reading from the speakers before us that in Lahore, over 60% is organic, degradable organic. So, content is different. We have scavengers, people in the street who collect the best of the waste. So what is left is waste of the waste. This is. And the third one is we do not sort at home. Perhaps we should not. We will come to that because we have a lot of experience with this too. Because what happens, I mean, since there are hand pickers or scavengers in the street, or how are you going to control it? How are you going to transport it? There are many different phases of the problem that we should see. And then the third one, our economical conditions are not the same. If you are in Japan, and if you have limited space, but if you have high per capita income, then you can have incineration, you can have gasification, you can have many other things to solve this problem. But at the end, you have to pay between $200 to $400 per ton of waste. This we cannot do it. In Turkey, we cannot do it in Pakistan. So we have immediately understood that we have to, this time, develop the technology which is going to solve our type of waste, our type of collection system, and our type of economical values. So what you're going to see from now on, I'm going to show you sometimes that this can only be done by our company. This, everybody can do it. And if you please have any ideas, any comments, please let me know, because I want to learn also from you, from your experience. This is how we start. Let's start. Now, can you see it? Okay. For the moment, we are I don't want to say, we are having under one umbrella to do everything related with the waste, except we are not involved in the transportation of the waste. We start after the waste come to the dump site or to landfill. And for the moment, we are working in these cities. Is there anything else going on in the other cities except the gas extraction from the existing landfill? There is not really much going on because of these special technologies that these kind of waste, these kind of economies can accept. So we are there. Let's go. Next, please. For the moment, when this presentation was prepared, we were dealing with 12,000 tons of waste in different cities. today it is, I don't know, over 13,000. Because what we do is, every year we are getting at least a few new sites. Every year is added to that. We can rehabilitate the existing dump sites. We can make it landfill out of the existing dump site. We can design and operate of landfills. We can establish sorting systems. We can establish again anaerobic fermentation systems for mixed collected organics. Here in this one, I think we are unique. We can establish RDF plants, refuse derived fuel for the cement factories. We can establish gasification and incineration plants. And of course, related with all of these activities, we can establish the energy production plants, because there are different energy production in gasification, incineration, and existing landfill, anaerobic digestion, etc. We can deal with the packaging waste if it is necessary, and we can recycle plastics, etc., which is not important for us. Anybody can do it. For waste heat utilization, we know how to utilize the excess heat. You will see it now. For carbon dioxide trading, nowadays it is not that much important, unfortunately, but we know how to deal with this. And what is more important than this, for the medical waste and industrial hazardous waste, we can build the necessary plants to get rid of these hazardous waste. Next, please. Now let's come to waste. Municipal waste. I have already told you that from the existing landfill, we can rehabilitate and extract gas and produce energy. After the material is transported, waste, we can establish the sorting plants by ourselves, but this can be done by many other companies. What is different is, since we are dealing with the waste ourselves, we know how strong machinery you need. We know, perhaps further, we have more practice than other producers of such machines. And from this, when we sort, we first try to get the degradable organics. Here the problem starts for the mixed waste, because in degradable organics, you have approximately 20% of other material you cannot prevent, because it is mixed collected. And with 20% other materials, debris, stones, sands, even steel, plastic, small plastics, etc., it is not easy to establish a fermentation system. And we have succeeded with this. You will see many of our plants, which are unique from this specialty, and plus the capacity point of view. We use dry systems of 4,000 tons of each tunnels. This is the biggest biologically which can be produced in the world. So we can do this. At the end, what comes out, as the other speakers mentioned, methane gas, you can produce electricity, And compost you can use again in the agriculture. If not, then there are other solutions in our system. We don't leave anything that this can be done here. If you cannot use the compost from one reason or to another, we have another solution to this. We can dry it, and we can use this as the raw material of our thermal solution. So, this one was, after the sorting, the first one comes out. The second thing comes out, if anything is left from the scavengers, we can take them out and pack them and send it to the related plants. And then, if you want to produce RDF, you cannot really trust all your system to production of cement, because your waste is coming every day. If cement factory is stopping for 1 month for maintenance, what are you going to do? You have to have this all in your mind. You can see how I'm speaking, because we are speaking by experience of many different fields. And then you can make from a part of it RDF, but still some left, and then you need a thermal solution. This is, and from the thermal solution, what comes out? Electricity together with the heat and ash, which is non-hazardous. Theoretically, in volumetric calculations, if you put 100, you get 10 as ash. 90 is turned into compost or electricity or recyclable materials. So, this is how our system is working. Now I can pass to our operation. Next, please. As you have seen, when I told you this story, this was the place that we came to visit. This was what we saw. You wouldn't believe, but you don't see it there. There's a tower there. Perhaps you see it. This is this center of Ankara. This place is only 5 kilometers from Presidential House, next to American Embassy. That's why American ambassador came to thank us, so that he can go out in the garden. Okay, let's go ahead. This was like this, and there were people living in this dump site, around 400, as far as I remember. And you cannot take them out immediately. You have to be very slow and patient, and of course, very helpful with those guys. And then this is the Minister of Environment and Mayor of Ankara. This was the next scene in 2 years' time. Okay. Let's go. One more. Now, I want to show you something. This was the first digestion plant we built with German technology. We had to tear it down. I hope there is no German around. But it's not their fault. It's our waste's fault. It's different. We have to tear them down. This was 7 meters, another 14 meters on the earth. So let's go one more. One more. This one I like a lot, because we are still receiving, this is the dump site, or landfill now, not dump site. We are still receiving waste. It is coming here to the sorting plant, and organics are taken out, and here the RDF is produced and put into the trucks. You will see them now. And from the methane gas, it is stored, of course, first cleaned, then stored. Then it goes into production units of electricity. Electricity is produced. Excess heat goes there to the shopping center. How come shopping center came to this place, next to the dump site? Because when you come here, you don't have any smell. although we are still receiving around 2,000 tons, 1,500 to 2,000 tons of waste every day. So people come here to buy tomatoes from our greenhouses, which is heated by the excess heat. Okay, let's go ahead. This is another site. Again in Ankara. In Ankara we have two sites. This time we are talking about 4,000 tons of waste handling, and the sorting plant, which can take up to 4,000 tons per day, with the digester units of 12. This is the biggest digester units you can see in the world. And storage and electricity production. At the same time, we have the gasification plant for the rest of it. And we are going to add some more gasification plant, which is under construction right now. Okay, let's go ahead. Okay, go ahead. I don't want to repeat many things. Let's go ahead. Next, please. Next. I mean, our friends have already talked about this, but let's go. Yes, next. Next. In different cities. This one is in Adana. So we have it in all the cities, in all different cities. Okay, let's go ahead. Next. 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 So you can see the production of electricity or established capacities for electricity in Mamak, 26 something. In Sinjan, again, the same amounts almost. Go ahead. Next. This is in Adana. Next. Konya, another city of over 1 million. Bursa, another city of over 2 million. And let's go. Next. A small city. We didn't want to leave this city for wrong hands, so we took this too. Okay, next. Another one. Next. So the total capacity of electricity for the moment is 100 megawatt. So for the hazardous waste, this is the plant. Next. For medical waste, we have two solutions. One of them is sterilization in autoclave. We do it in Adana, in Antalya, and some other cities. But we really don't like sterilization too much. We prefer the thermal solution. In thermal solution, you have to bring it up to 1,100 degrees for 2 seconds, all the gases. So it's really a good solution, final solution. Whatever comes out is really non-hazardous. Anyhow, we have both systems. So we are trying to convince our government also to find a way to solve this problem for Turkey. So we have visitors each year, around 12 to 14,000 of visitors. From Turkey, around 10,000. From kindergartens to universities. And from abroad, around 2,000 to 3,000 each year. So we have a lot of activities with packaging waste, this, that. Okay, next. Next. I told you about greenhouses, so you will see some applications. It's good. So we are selling these tomatoes. So what is good? Even the people, even for the children, when they come, they see these tomatoes, they understand that we are using the heat, excess heat, from the waste, from the electricity production, plus we are using the excess carbon dioxide, which plants need. Let's come back a little bit. And then, with this, we are producing, together with some water and some other material, we are producing tomatoes. And all these leaves and whatever the green material comes out, it goes back again to anaerobic digestion to become electricity. So they can see the cycle. Okay, next. We can produce strawberries 4 times more per square meter because of our different technique. Okay. Now, there's another team, because our company is technological research and development oriented company. So whenever we go into a subject, we go deeper. For example, in this production of potatoes, we are using hydroponic systems. Usually when you get one small potato, to get other potato seed, you have to plant it, and you get 6 to 8 new potatoes from one. We can get 30 to 100 from the same potato by these techniques. And we have enlarged them. It has been in industrial capacities now. So let's go ahead. I think that's, the real potatoes now from our seed. I think that's good enough. So let's go to the second presentation. When I tell you, we built this, we designed this, what I mean is this. When we are designing a plant, we are starting from the design of the concept, design of the process. We design the process, how you can do this, the process itself. Then we design the plant. Then we design the machinery. Then we manufacture the machinery. And we have seen that in Turkey, especially when you come to anaerobic digestion, gasification, these are high-tech technologies. I mean, gasification plant is not different than refineries. It's more difficult than oil refineries, because oil is a constant material. Our material is not constant. It keeps changing. So our refinery is really more complex. So it's not easy to operate these units. So in Turkey, what we do is we have the ability to finance and build the plants and operate them continuously for the municipalities. So that means our ability starts from process design to finance and build them and keep operating. And also new innovations are immediately added to these operations. This is where we stand. Okay, then some people, later on I noticed, when I said we are building the machinery, but they see the plants. When we talk about gasification plant, it is 200 meters long, 34 meters high, and almost 100 meters for a twin unit width. It's a refinery. How you can build this? Where do you build this? I noticed this, so this is one of our sister companies. I put this also into our presentation. In this company, it's a casting and machining factory plant in Turkey, in Ankara. Actually, we have 4 plants next to each other in the same organized site. We can cast up to 200 ton per piece casting, and we can machine this. We can lift this 200 ton piece, put it, actually 250 ton, put it on the machine, take out the 50 ton, leave 200 ton perhaps. This is our plant. You will see it now. Let's go ahead. You can see that there are 4 plants. Let's see. Let's go ahead. Let's go ahead, fast. Where do we sell? Okay, let's go ahead. Okay. Okay. Okay, you see the 4 plants were located in Ankara. Why you see all these harbors? Because we are selling 95% of our production to Europe, 25% we are selling to machine parts to Sweden. The rest is Germany, France, Spain, United States, Canada, South Africa, China. And these are some of the companies. For example, this is in crushing business. Sandvik from Sweden, Thyssen from Germany, USA. These are our customers. Some of them are producing all their machineries in our plant. Let's go ahead. This is in cement industries. We are working for them. In energy, we are working for them. Let's go ahead. Go ahead. So you can see some of the pieces. Let's go ahead. Okay. Siemens casing for turbine produced by us. Okay. So this is our machinery part. A film that you can see them all. I will still be here to tell you what is what. Only this? Okay. Okay. You can see this is a 4,000 tons per day. Sorting plant is receiving the waste as it comes, day and night. This one is working 24 hours a day. It goes into a sorting system. We are using very special material here because it's not easy. The sorting started, bags are opened, sorting started, and the first thing comes out is organic, which can contain up to 20% debris, like this. A magnet collects the metal, goes into premixing, pumped into different tunnels of anaerobic digestion. Each tunnel is 50 meters long. From the other side, compost is coming, dewatering is there. From each of these tunnels, we are getting 20,000 cubic meters of gas from each tunnel. Then compost comes to the compost plant for drying, and then later on for the separation of the debris and other materials from the compost. You can see the compost on the left side and the debris on the right side. And the software system to run this from the control office, this software is prepared in-house. They see the factories. You can see in a different office, they just watch the operation run by the computer, and wherever is necessary, they touch. The gas is coming from the anaerobic digestion. They are cleaned from hydrogen sulfur, stored, and electricity is produced and given to the main grid. We come back now. Organic part is taken out. The other part is coming out. You can see it's more dry now. There are some plastic, whatever is left, so we put a few men rather than automated system. We don't need that because there is nothing almost left. As you can see, pets are taken out. This is up, so it's put down. They are packed and sold. You see, it looks too much, but there's actually percentage-wise nothing. the cost does not even cover the revenue, or revenue does not cover the cost. It's automatically packed. Then, still the material is flowing. Metals are taken by the magnets. This time, some of the material is diverted to production of RDF. The metal is crushed more, and then it will go into another phase of unuttum Erdoğan ya. Another phase of screening. Some parts will be taken out, but this will go into, again, thermal unit, gasification. Nothing will be left out. This is the cement, RDF. It goes directly into a truck, squeezed, and goes to the cement factory. You can see. Then, whatever is left from compost, from RDF production, and the rest of the material coming from the sorting plant goes into gasification, which is again built by us. And in gasification, you don't see anything. You just see the material taken from the bunker and put from a hole. Then what you see is only the ash coming out. This plant is running theoretically by 3 people. One is playing with the joystick. The other 2 is watching the computer screens. And this is again completely designed, built. Software is again in-house by our people. Ash is coming out. You can see how little space is left for ash. Of course, when we talk about this thermal unit, 3/4 or 2/3 of the plant is cleaning the gas coming out of the gasification or thermal units. Yeah. And from the heat obtained or from the syngas obtained, we produce electricity. The electricity production is done by organic Rankine cycle, and the production of, including the turbine, the production of full electricity system is done by our company. For the turbine part, we are working together with an Italian solution partner. All these electrical cabinets, software, etc., all of them are designed and produced, built in our factory, in our plant. Burada dursak olur mu? Duralım mı bence? Ha? Okay. Bir de şurayı görsün. Okay, I think we can stop here. Okay, I thank you for all of you to listen to me. If you have any questions, I'm ready to answer. If not, I thank you once more.
Thank you, Mr. Ali Kantur, for providing us an insight that may help us to learn from your experiences in Turkey and solve our waste management problems. Now, I would like to conclude the session. Thank you so much for your patience.